So what we still have left is to finalize the problem of phase transition specifically. And I will remind you where we have finished our last lecture. We had T and P, and we were looking on the behavior of the chemical potential. And what we have seen for the chemical potential, that in one phase there was one surface of a chemical potential, and in the other phase would be an additional behavior for the same chemical potential. And the phase transition, or more specifically coexistence curve, was defined when there is equivalence between the chemical potential of phase A, or subsystem A, and the chemical potential of subsystem B. Basically, this line over here, right? Now, if we look, for example, on the behavior of the chemical potential as function of P for a specific T, okay, so it would be an isotherm, what we can see that, well, in one phase, it is linear, not linear, but it's a continuous function. In the second phase, it's also a continuous function. And it's continuous everywhere because there is equivalence between the chemical potential of phase A and phase B. But specifically, at the coexistence curve, so on this red line over here, we see some sort of a cusp. Okay. What this means, the chemical potential itself is continuous. But actually what can happen that exactly the phase transition, the derivatives of the chemical potentials with respect to P or with respect to T, I can plot the same graph when I plot the chemical potential as a function of the temperature for a specific pressure. Okay? But what we see that at the phase transition, the chemical potential can perform some sort of a jump. Not the chemical potential, but its derivative. And why this is so interesting, why that I will have some sort of a discontinuity for d mu dp, which is a derivative of the chemical potential with respect to the pressure, or of the same chemical potential with respect to T. Why is this interesting? So what actually jumps? So I have some sort of a discontinuity in the derivatives. So let's see why actually from the physical perspective it might be interesting. How can I write down? So I have generally there the derivatives, but where I can obtain it from, what equation I can use in order to see what are those derivatives explicitly are. Okay? I know that they can perform some sort of jump, right? So let's see. I remind you that we derived the Gibbs-Duhem equation. Okay. What does Gibbs-Duhem equation actually looks like? It's 0 s dt plus minus v dp plus mu and d mu. Okay? So if we have only one type of molecules, n is the number of the molecules, number of moles of the molecules, we derive this equation. Okay, so let's see what happens when T is constant. So we're looking on the isothermal process. So or we can look on the process when P is constant. But generally, what we have is that d mu equals S divided by N dt minus plus V divided by N dP. Okay. So let's go into the definitions of specific entropy and specific volume, which is basically entropy per particle, okay, and entropy and volume per particle. So we have S, it's a big S divided by N, and small v, it's a big V divided by N. And what we see is that d mu equals minus S dt plus V dP. And more explicitly, this is the derivative of mu with respect to t. And this is the derivative of mu with respect to p. So what we obtain is that d mu dt equals minus s. And d mu dp equals the specific volume. Okay? This is when p is constant. This is when t is constant. Okay, so we know that those derivatives are not continuous. Which just basically means that the specific volume or volume per molecule is performing a jump when we are crossing the line of phase transition, or the specific entropy. The entropy per particle is performing a jump. Or they may be continuous, right? So we can actually use the existence of a jump or a continuous transition as some sort of a definition for a phase transition. We can say a jump in V or S, okay, is when crossing the coexistence line specifies a phase transition of the first order. So when I have a jump in the derivative of my chemical potential, okay, I call this process or this type of phase transition first order first transition. When there is no jump, and basically the derivatives of mu continuously transit from when I'm changing from phase 1 to phase 2, okay, what actually start to happen, well, what I call this process, I call it process a second order phase transition. Okay, so there is first order and there is a second order phase transition, which I will write over here. A second order, or we'll say continuous phase transition occur when d mu to dp or d mu to dt are continuous at the coexistence line. All right. Now, think of it for a second. What actually we have here? Basically, we had entropy per particle. We can say, well, the entropy per particle is the amount of how much it actually moves. How many, on average, how many how many states it has accessible to it. If you're thinking about a particle in continuum media, how fast it just basically fluctuates around. Okay? This is somehow related to the entropy. The volume, what it signifies, the volume is I'm looking at the particle. I had a lot of particles. And I'm looking on the average volume per particle. Is it small? Is it big? It's not the volume of the particle itself, because the particle itself, for any sake, can be pretty small, right? But it's the volume plus some free surface around it, all right? Now, so what we have now, at the phase transition, something peculiar happens. The specific volume, the volume per particle, shrinks or explodes, okay? So think about like what happens in water. We heat water up, the water has, the water molecules have a specific volume around them, how they can move, and at some point this evaporates. You're looking already on a gas. It's not exactly a gas without interactions. There are some sort of interactions, but momentarily the volume of the particles, or the volume between the different particles, is jumps significantly. What we see is that the particle beforehand occupied just this specific square, and moment after, the square just growing. It's not that the square changed a little bit. We had almost like an explosion of the free volume per particle. It's something that actually can be recognized, and you see it. You see this transition of water to vapor, or between water into ice. What we see for water into ice, so the particles were floating around, they were moving almost free, not exactly freely, but they were allowed to move. And the second as we cross this temperature, and the system is basically freezes up, the particles are stuck. Okay? We don't have exactly crystal, right? But in ice, it's already solid, and the particles, well, they're just wiggling around themselves a little bit, but they're stuck, and everything is basically stuck at one single place, right? So we have a jump in the entropy. This is exactly what happens in nature, as you see it. So we have here a general perspective, mathematical perspective, but this explains precisely what happens in nature. Those specific jumps that we observe, okay, they happen on molecular level. So what actually happened at phase transition, the whole system behaves differently. But the most significant parts are actually occurring on the molecular level, and we can see them today. Okay? We see that the molecules are just frozen. This transition to ice is significant. All right. How can I find those transition lines? So let me rephrase my question. If I have a state function, so I have some sort of a connection between, for example, the volume and the pressure. Okay? I have a state function that describes to me how the system behaves. How can I find those explicit small points? Because we already learned the Gibbs phase rule, and there I can see that there is always existing a line when the phase transition occurs. And my question is, how do I find this line, right? So when I have v as a function of p, and we'll see this on our example of van der Waals intuition, or p as a function of v. And this function is a state function. So it describes the equilibrium state for a specific volume and a specific pressure. Okay? How I find those phase transitions? So we can just plot it. Okay? We'll plot v as a function of p for specific isotherms. So each line here is for a very specific temperature. This is a specific volume. And what we see, well, usually for high enough temperatures, it almost doesn't matter what the pressure is, there is some sort of a behavior. And usually, V, not usually, but we always will see that V is always decreasing as a function of P. Why is that? We have shown from the stability criteria that dV dP is always smaller than 0. This is always what have to be consistent with the stability criteria. Otherwise, we do not describe equilibrium process or process that actually now is in equilibrium. What will start to happen as we decrease the temperature, the line goes down. At some point, I will have an inflection point, so basically the derivative is almost 0 over here, okay? And then what will start to occur is that I will have a V, and then again I will have a different V. So I will see a jump delta V as I'm changing my P, right? This is what I expect. I expect that for two different pressures, there should be very different specific volume, even when the pressure are very, very, very close together. This transitions, I will start to see explicitly where I will start to see them at the phase transition point. There should be a jump in the volume as a function of P. And the one thing to notice is before the jump, there should be the derivative of the volume with respect to the pressure is negative. After the jump, the derivative of the volume with respect to the pressure is also negative, right?
Excuse me?
Yes?
The third line's derivative is continuous or?
So everything is continuous except this point over here. Okay? It always continues. It's only at the points of the phase transitions there should be some sort of a jump for the volume. And then the derivative becomes infinite, basically. Right? Now, and the thing to remember is that the derivative is continuous and negative at every point except those points where the continuity is lost. So for example, I can have P and V that will behave in the following fashion. So I can have a behavior of B which is decreasing as a function of P, and then I can have a jump, okay, which is not downward for the volume, it's actually upward for the volume. I can have this behavior, for example, for water, right? And it doesn't stand in a position to my stability criteria. Why? Because here the derivative is negative. Here the derivative is negative. Here what happens to the derivative? Well, it's basically undefined. So I don't really care. Okay? But the stability criteria, away from the critical points, the phase transition points, is basically always saying that the volume decreases as a function of the pressure. All right. Now, there is only one single point when there could be a lot of points when I will have a jump. We'll see it on the example of the van der Waals gas. But there is only one single point when the derivative of V is 0 with P. Okay? And this is the point of the phase transition, of the second order phase transition. Okay, so let's derive exactly for those points when I have a jump, in the volume and jump in the entropy. Let's derive an equation for this coexistence line. Okay, so what I'm having here, let's plot P and T. Okay, and in this P and T, for example, I have a coexistence line. Coexistence line, okay, which describes me where the phase transition should occur in terms of the pressure and the temperature. And I want to actually, well, find this line. We'll write an equation for this line. This is what is known as the Clausius-Clapeyron equation. Okay. We know that exactly on the line, on the coexistence line, what happens? I have an equivalence of the chemical potentials. So the chemical potential of phase alpha at T and P equals to the chemical potential of phase beta at T and P. d mu, no matter for what chemical potential, we already have shown this, it equals minus S dt plus V dP. Okay, so there is no difference in the chemical potentials when I'm stepping on this line over here. Okay, there is no difference between the chemical potentials of phase alpha and phase beta when actually I'm going exact on this line over here. So d mu alpha equals d mu beta when I'm on this coexistence line. So what we can have that minus S alpha dt plus V alpha dP equals minus S beta dt plus V beta dP. Okay. Just basically, I write this equation for phase alpha and for phase beta. Okay, so what can obtain from this is that what is dP divided by dt. Okay? So I take everything to all the dP's to one side, all the dP's to the other side. I multiply everything by s's and v's, and eventually what I obtain is that it equals S alpha T and P minus S beta T and P divided by V alpha minus V beta. Okay. What it means, or let's write this as dP by dt equals delta S divided by delta B. And this is, for the first order phase transitions, is non-zero, and delta V is also non-zero. Exactly on the coexistence lines, there is a difference between the specific volumes of the two phases. And there is a difference in what? In the specific entropies of the two phases. So this equation is very well defined, but only for the first order phase transitions. For the second order phase transitions, we cannot derive an equation for a line. And actually, why is that? Because, well, as we will see in the following, there is only one point where occurs a second order phase transition. So there is only one point when this derivative is actually zero, right? All the other points we can have a jumps in the volume. But only in one point where there is the derivative of the volume when going from one phase to another, it's excuse me, it's when the derivative is actually going to zero. It's not an equation or differential equation, if I has to be correct, for the second order phase transition. But for the first order phase transition, this equation explicitly gives us the connection, or how P defines as a function of T at the phase transition coexistence line. This equation have a name, and it's called Clausius-Clapeyron. Clausius okay. Very nice. All right, now let's continue with our investigation into the area of definition of the phase transitions. So what I'm going to describe to you now, it's called a Maxwell construction. For phase transitions. And why do I need this at all? Well, think of when all this was derived. We're talking about the 19th century. And people do not really understand, well, they have extremely huge arguments about the molecular theory, okay? So they are not completely convinced, or they're not convinced at all about the existence of atoms, the existence of small molecules. The molecular perspective is not really winning over there, right? So, but they do see things that describe the matter as in different phases. They do see that the matter can be solid, can be fluid, it can be gaseous, okay? And they perform a lot of experiments explicitly doing some stuff with gases. They measure pressure, volume, etc., etc., etc. Now, afterwards, they derive equations of state, okay? They derive how the energy behaves with temperature, and with entropy, and with volume, and with pressure, or all of the other descriptions. They can derive the Gibbs free energy, or the enthalpy, or the Helmholtz energy, and they have models of what actually happens in the system. For example, one very familiar model is the van der Waals equation for the gas. But in general, they have different models of how things should be behaving at different phases, at 4 different phases. And for example, they have A, the Gibbs free energy. Okay. And assume that they had a specific formula, mathematical formula, that they propose for this Gibbs free energy. And now what they want to do is basically to construct the behavior before the phase transition, after the phase transition, and at the time of the phase transition itself. So if they had A, and they plot it as a function of V. Why? Well, it's some sort of a Gibbs free energy. They can measure it. Okay, you remember why we derived all this, because experimentalists eventually want to measure specific quantities, and they see that for small volumes, specific volumes, it's decreasing. Okay. For higher enough volumes, it's also decreasing. Okay, so their model, this is what it describes for low volumes, and this is what it describes for high volumes. And in the middle, something peculiar starts to happen, okay? We don't really know what happens here. And the model starts to predict some, for example, that A is growing as a function of V, or its derivative is doing something peculiar, okay? Basically, in this area, when the model misbehaves. What I mean by misbehaves it produces specific behavior which is not consistent with stability criteria, for example. Okay. Maybe not exactly at this point, maybe somewhere here, the derivative of A with respect to V is, or the second derivative of A with respect to V is positive or negative. And remember, we have a very strict consequences that are coming from the signs of the derivatives or the second derivatives. Why? Because they are actually defining the stability of the equilibrium. Okay, so what they know is that there is a nice predictions that's working over here, there is a very nice predictions that's working over here, and something not exactly clear and nice that's happening over here because the model that's not working. Why it's not working? Because the model assumes homogeneity of the matter, right? Think about it. Okay? They're looking on the matter. They do not know, or they do not assume something about the molecular foundations, right? So they have a general equation for what happens to the matter. And when the system is in one phase and deep inside this phase, everything is pretty much homogeneous. Okay? When you're in other phase, everything is very much homogeneous. But when you start to be at the very close to the phase transitions, the material is not homogeneous anymore. Right? Think about the boiling water. Okay? It's not that all the water at once they transform from water into vapor. What you see appearance of small bubbles of vapor inside the kettle, right? If you look closely, you will see that for some specific temperature, and the temperature is still below 100 Celsius. Already at 70 Celsius, you would start to see appearance of small bubbles. Where they come from? They come from fluctuations. You're already close to the phase transitions, right? But the material itself is already not homogeneous. It has bubbles of air inside of it. So it's not only water on one side and air on the other. It's water and some small particles of air already inside. So there is mixture of phases. Close to phase transition, we already start to see that the material is not homogeneous. Okay? There is some sort of a coexistence going on inside. And exactly here, all of those continuous models, okay, that they try to derive the state functions, they assume homogeneity. In this region where phase transitions start to occur and it shows non-stable behavior, it's basically because the system is not homogeneous and the state function like energy, free energy, enthalpy, they're already failing to produce the correct result. So Maxwell, well, probably understood everything already back then. He proposed something which is pretty clever. He said, well, I cannot exactly or cannot rely on the behavior of the state function at the phase transition itself. Why? Because, well, it basically shows me something which really, really weird. Why it's weird? Because the material is not homogeneous anymore. So what I can do, can actually say, well, I know that at equilibrium, at the phase transition, I have an equivalence. What kind of equivalence I have? I know that the pressures of phase alpha and the pressure of phase beta, okay, is exactly the same. So here I have a volume V alpha, and here I have a volume V beta. Okay. I know that exactly at the phase transition, the pressures are exactly the same. What is the differential, this is A, of the free energy? So dA, we know, is minus S dt minus P dV plus mu dN. Forget about dN. Let's concentrate on, forget about the dt. We are looking on isothermal behavior. What happens as we change the volume? The volume is changed, but the temperature is constant. Okay, so we know that dA dV at constant temperature equals exactly this guy. It equals minus P. So the slope here is minus P. The slope over here is minus P. So if I have a phase transition, so here the phase transition starts, here the phase transition ends, okay? The slope here should be constant and equal to the slope over here. So instead of going into a continuous description, which is basically wrong, what should I do exactly at the phase transition? Or how would they define a phase transition? I should draw a straight line which coincide with my behavior over here and coincide with the behavior of A over here. What I mean by coincide? I mean that the slope is equal, right? And this is my approximate true behavior of the system. It's not true. Why it's not true? Because all the behavior in this region is not true when I'm looking on state functions that describe me homogeneous phases. There is nothing homogeneous in the system over here. There are a lot of airs, bubble airs, and a lot of water, or small clusters of ice and water. So I cannot use this behavior anymore, this description. And what Maxwell proposed is instead of using the regular state function, what should I use at the phase transition? What should I use at the phase transition? I should basically connect the different parts of when the phase transition starts and when the phase transition ends by straight line. This was his proposal. Okay, I've already done it here. So let's see where it leads us. How can I now write the equation for A at this specific region? So I know that P of alpha, T and V alpha, equals to P of beta at T and V beta. So the equation of this guy is the difference in A divided by the difference in V equals to minus P. AT V alpha minus AT V beta divided by V alpha minus V beta. Okay, so this is the difference in the y direction divided by the difference in the x directions. It produces the slope of the linear function that connects the dot over here to the dot over there. Okay, which is basically equals to minus P. P where? P here or P over there? But we know it's exactly the same P. It's exactly the same pressure. This is a condition of the phase transition. Okay. So from this equation, what we have is that A plus PV alpha equals to A plus PV beta. Okay. But what is A plus PV alpha and what is A plus PV beta when we have only one component? Okay. It's a Gibbs free energy, and it basically says that mu alpha equals to mu beta. And this is exactly our condition for coexistence curve, right? The condition for coexistence curve, we said, well, what should happen at the coexistence curve, that the chemical potentials are exactly the same. Now afterwards, Maxwell wanted to use this exactly condition in order to show or basically describe how the system behaves when it transits from phase alpha to phase beta. Okay? And all this equation for the Helmholtz free energy, A is basically based on this condition of equivalence of chemical potentials. Okay. Let us see what happens for the van der Waals gas. So van der Waals gas, it's a model for the behavior of gas molecules when he actually had in mind that, that there are molecules, that the gas can be described as some sort of a molecules that interact with each other. Okay? Because before van der Waals gas, the only thing that we had is PV equals KBT. Okay. This is the equation of the ideal gas. And the ideal gas, which connects pressure to the volume, and for the ideal gas, there is no phase transitions, right? Plot pressure, or the pressure as a function of V, pressure as a function of V, or the volume as a function of pressure, okay? And the only thing that you will see that, well, it always decays, so the system is always stable for any constant temperature, okay? There is nothing peculiar happens over there. The system doesn't have a discontinuity points. The derivatives are always well defined, except, well, when V is 0. But what is V 0? It's unphysical. Okay. So the ideal gas does not describe any sort of phase transition. It doesn't matter how increase the temperature, decrease the temperature. There is no jumping points. But what they see in experiment when they measure the gases, okay, they suddenly start to see, well, the fluidization occurs, I can see phase transitions. Ideal gas, it's a bad model. Why it's a bad model? Think about it. Ideal gas assumes, well, I have a lot of particles. Oh, now we know what is the ideal gas assumes. Okay, back then they didn't really knew that. So I have a lot of particles in a box. Those particles never interact one with another. Never. Okay? They're always interacting only with the box, with the size of the box, with basically the constraints that prevent them from exit the box. This is the only sort of interactions that they can have on one another, but they do not feel each other. And this is why phase transition cannot occur over there. Phase transition is a property when the molecules start to do something together or stop doing something together. Either they are somehow correlated, or either they are not correlated at all. So for ideal gas, when they do not feel each other, never feel each other, not in any way, I cannot see any phase transition. This is why the ideal gas failed to reproduce the experimental observations. Van der Waals proposed a different model. Okay. So the model of Van der Waals went as P equals KBT divided by V minus V, okay, minus A divided by V squared. A and B are constants. Okay, A, B, and constant. KBT, well, it's temperature or energy. V is the specific volume. And what we see over here, we have this guy. Where this guy is coming from? This guy is coming from by saying, well, the volume cannot be too small. I cannot decrease the volume too small. Here, well, there is no restrictions on the volume. Here, but then saying, well, the particles start to feel each other when I decrease the system, when I press on the system and become smaller and smaller and smaller. Okay, at some point, the gas molecule starts to feel their neighbors and they do something. What do you mean they do something? Well, they pretend they push backwards on their neighbors, and then the pressure have to be higher, right? This is this particle over here. This term, minus a divided by v squared, comes from, well, now we understand that it comes from variable expansion, but basically it says the particles themselves have some sort of interactions. They attract each other a little bit. Okay? This is some sort of an electromagnetic interaction. So it's very easy for us to understand this equation. Okay? Of course, there is free volume, and you cannot press the system too much, because the particles, well, they will just kick their neighbors outward. And at some point, the particles are actually keeping their neighbors also not too far away. Why? Well, because there are some sort of electromagnetic interactions between the particles. But think about 150 years ago, when people had no sense about the molecular perspective, or atoms, or everything is continuous. This was very, very clever, and he got a Nobel Prize for this. All right, so what we will see for this equation? He got the Nobel Prize not only because it was clever, it also had a very good quantitative predictions for the behavior of the gases. Predicts existence of phase transitions. So we plot P as a function of V. Okay. What will we see? Well, at high enough temperatures, so each line is isothermal. For high enough temperatures, this guy decays basically like the ideal gas. And it's clear, when temperature is very, very high, everything is very hot, the average distance between the molecules in the gas is huge. They do not interact with each other almost. And the behavior of the van der Waals gas and the ideal gas is exactly the same. We start to decrease our temperature. And at some point, we'll see that the derivative of P with respect to T became 0, right? There is some sort of an inflection point. Okay, very interesting, one would say. What happened next? So this is higher T, lower T, lower T. We decrease the temperature a little bit even more. What we see over here is that this behavior starts to appear. What do we have? So we have here an inflection point, and at some point we'll have a maxima. Okay, so you have a maxima, you would say. Who cares? This is the behavior, this is the great van der Waals prediction, but this is bad. Why it's bad? Because at this area over here, okay, this area over here, the derivative of P with respect to V is what? It's positive. Okay, it's positive. So the system here is not stable. Exactly at this region, doesn't go to 0, of course, right? But at this area, the system is not stable. Because we have here dP dV is greater than 0, and we know that in order for the equilibrium to be stable, dP dV should be negative. Very bad. Okay. Why bad? Well, the system is not stable. This situation cannot occur in nature, as we understand nature. Well, let's throw the van der Waals equation away from here. It's really, really bad. But no, this is not what we are going to do. Because this was, from their perspective, they understood that something very interesting happens here. Okay? Something really, really interesting. So here, and when they look on the experiments, well, they see small volume. There was a liquid phase over here started to appear. And a gaseous phase started to appear. So there are somehow different phases start to appear, and the transitions between the two phases occurs exactly when the equation of state describes a non-stable behavior. Okay? So we can now go backwards to the Maxwell construction and ask ourselves, well, how can I relate this behavior or this construction of Maxwell to the construction that I have to something that I have over here? Okay? So clearly this equation fails to describe the true situation. I should use something different, and this is Maxwell construction in order to describe what happened in the phase transition. Okay, so how it works for the Maxwell construction. Basically, what we need to do is here we found an equivalence of what? I'm sorry, we have found an equivalence of the pressures, right? Of the P's over here. So there was a pressure here, there was a slope over here, and there was a slope over there. And we said that when the slopes are equal, we draw a straight line between those points. Okay? And the slope is exactly P. So we should find 2 points. One is over here, so V alpha, and some other point. One is over here, V beta. Okay? And those 2 points will symbolize when the phase transition starts, okay, or can start, and when the phase transition ends. Now we assumed here, okay, what we assumed, that the pressure, this is the Maxwell construction, that the slope of A with respect to V is constant over here because we've drawn a straight line. So here is the slope is P minus P, here it's minus P, and minus P. Okay? But remember that dA equals P dV. Okay? P dV or minus P dV? Minus P dV. Okay? So when I'm constructing A, okay, so let's integrate this guy, integrate this guy. So A at some point VB minus A at some point, this is V alpha, this is V beta. A at some point V alpha is equals to the integral of V alpha V beta dP dV. Okay. But we know what is the difference of this guy was. Remember that we had A V beta minus A V alpha divided by V beta minus V alpha, okay, what equals to what? Minus P, constant P. P alpha or P beta, it doesn't really matter. So if we divide this integral by V beta minus V alpha, what we obtain that the Maxwell construction stated the following thing: an integral from V alpha by V beta of P dV is equals to P alpha multiplied by V beta minus V alpha. And this equation gives us exactly the condition or the Maxwell construction for this curve P and V. Why? Because we are saying what is integral of from V alpha to V beta of P dV. This is basically this area over here. Okay. But this is from one side. But it should be equal to what? P of alpha multiplied by VB minus V alpha. This is also an area, but an area of what function? It's an area of this function. Okay? So we have a constant P alpha. Okay? And what we claim that the area of this rectangle that have a height of P alpha and a width of V beta minus V alpha is equals to the integral. Okay? So the condition for the Maxwell construction in the PV diagram goes to plot P as a function of V. We find the area when we have a non-zero, we have a positive derivative of P with respect to V. And we draw a line. Okay? We draw a line where this total area is equal to 0. Why it's equal to 0? It basically says, well, the integral of this function equals to the integral of the constant function. And what Maxwell have actually done, said, well, I don't know about this part and this part. Something really peculiar happens here, so just replace it. This is Maxwell construction. We take P before the phase transition starts. We take P after the phase transition ends. Okay? And the middle, we just draw a straight line. It was a straight line with some specific slope over here, and it's a regular straight line with slope 0 in the PV diagram. So, So the behavior of the van der Waals gas would look like as it was predicted by the equation. This is P, this is V. So it will just generally decrease as a function of V for high enough T. It will have an inflection point where a second order phase transition will occur. And below that, it will have, we will just change the behavior and plot it very, very differently. Okay. What happens here is that we have straight lines. So this function, we have to take our original equation of the van der Waals, which gives us the prediction of a phase transition, but we cannot use it at the phase transition itself. Why we cannot use it? Because it has a non-stable behavior. It predicts something which is not stable. So we replace this non-stable behavior by constant P. Okay? So we have a constant P here. It does not change. It does not change. The volume have to grow. The volume have to grow. And at some specific point, the volume starts to decrease again. What happens over here? Why the volume is not changing in this region? Or why we just try to describe this like this? Think about it in a physical perspective. So I was in the fluid phase, and I arrived at this point. This point, this is V alpha. I have it as V alpha, and this is V beta. At this point, bubbles start to appear. I was in fluid, and this point, the first tiny bubble appeared in the system. When it's already there, the system stops being homogeneous. Although I'm trying to expand my volume, but the bubbles have smaller volume or larger volumes. So the volume is growing, but the pressure stays the same. Why the pressure stays the same? Because I have bubbles. Okay? I continue to expand my volume, but I'm expanding my volume not because I'm trying to push the system outwards. I'm doing something inside the system itself. So now more and more water becoming air, right? I have more and more bubbles, less and less fluid, more and more bubbles, less and less fluid, until at this point I have no fluid and only bubbles. And then the system behaves normally again. It behaves in a gaseous way again over here, right? I'm sorry. And this is quite neat, that you can obtain this behavior without knowing anything about the molecular structure. Well, of course, van der Waals was smart because he predicted that we have molecular structure inside, molecular behavior. But if you think of this in the perspective of state functions, when everything is homogeneous, this is why what we assume so far, this fails. And how it fails? Well, you have these discontinuities. You have to have them. Otherwise, something fishy occurs and the system is not stable. Okay? Okay.
I have a question.
Yes?
We have a temperature that have inflection point.
Okay.
If we code it only a little, like t minus t.
Okay, so like for this graph or for this graph?
For second.
This?
Yeah.
So you want to go upwards a little bit?
No.
Downwards?
Only a little bit.
Uh-huh.
Will V alpha very near to V beta.
Mm-hmm. Yeah, but still we will see this.
So there is a minimum delta V?
Yes. Yes. Exactly. And this is described by, well, your bubble have to be macroscopic. It's already dependent on the chemicals of how the bubble is constructed. But at some specific point, you cannot have bubbles. Well, or the difference between the air molecules and the water molecules at specific pressure is not different. So you cannot just have bubbles. That's it. Or you cannot have water. You have only gas. I will describe you in exactly now, because this was my next point. So thank you for asking.
Well, for different types of molecules, what's the difference in the equation? Is the A different?
The A starts to be different, and the B starts to be different. So they had, what they started to do 150 years ago, they started to plot a lot of tables. They had gas, argon, or whatever. And they start to measure its behavior, and from this behavior they started to quantify B's and A's. And they could do this for a huge number of gases. You have tables, very, very long tables, with specific A's and specific B's. Now, but this is an approximation, because actually what you should have over there, you should have something divided by V to the third, and V to the fourth, etc., etc. So you need all the expansion in terms of V, and also here. Because, well, you have only single parameter, but you also need here something, well, that would be dependent on V itself. But this is an approximation, but it works extremely well. Okay, back to your point. Let's look on the TV diagram. So we have V, and we have T. Okay. And in this TV diagram, we know that for low enough temperatures, I can have, here for example would be fluid. Okay, I go at the same temperature, and here I will have gas. I can draw lines. Okay, on this part of the line, I have fluid. On this part of the line, I have gas. I have a jump. I have a big jump, okay, between one phase to another, because here I have some sort of a mixture of gas and fluid. And if I continue to draw this line over here, at some critical temperature, if I go above, I don't have a difference between the volume of the gas molecules or the fluid molecules and the gas molecules. And this is exactly what you're trying to say. Because this point over here is this point over there. And if I go to a little bit higher temperatures, there is already no jump in the volume between the fluid phase and the gaseous phase. You cannot discriminate between them both. They will see exactly the same to you. Okay? It's fluid or gas, you don't really can tell right now. here we'll have fluid. Here we'll have gas. Okay? And in the middle, we have a mixture. So think about it. So you're at specific temperature, and you're changing your pressure. You're changing your pressure. You're doing something. So your volume is increasing, increasing, increasing. This point, you have only fluid. You keep changing something else, and in order to have only gas, your volume have to jump to this position over here. Okay? And this is the first order phase transition. So when you have these differences between fluid and a gas and some mixture in between, okay, you have a difference in the volume, right? Because here is your V alpha, here is your V beta at constant temperature. Okay? So you're at the constant temperature, and in fluid you have one volume, in the gas you have another volume. In between you have a mixture because you have a mixture of bubbles and water. But as you increase your temperature, at some point there is a maxima. Okay? So there is already no difference between the water or between the fluid and the gas. And exactly at this maxima, this is when there is no difference between the specific volume of the fluid and specific volume of the gas. And we remember what happens when there is no jump at the specific volume. This point of a maxima is a phase transition. Phase transition of second order. And if we thought that something mysterious happens at the first order phase transition, actually something really peculiar happens at the second order phase transition. Because we're used to first order phase transitions. Because when we boil water, we see those bubbles, right? We see those bubbles, and the water, well, it reaches 100 temperatures, there are a lot of gas inside, but we still have water, right? Because the transition to the transition to the gaseous phase, it started by local fluctuations. Some of the water transformed into vapor, and some of the water is still water. But the second order phase transition says the following: your water, you would see no bubbles. Okay, so you would look on your water, it would be just calm. Okay, but the temperature will rise and rise and rise and rise and rise. No bubbles whatsoever. At some point, at once, pretty fast, all of the water will evaporate. It will just transform to gas, almost instantaneously, without bubbles, without heating up, just like this. This is something that is a little bit counterintuitive, but it occurs to nature. Okay? You have an abrupt transitions when you have only fluid, but pop, you have a gas. Well, maybe not fluid to gas, I haven't observed it, but you can see this with resistance. Superconductivity occurs in this way. So you cooling the temperature and you measuring the resistance to electrical current. And you have your resistance and it basically decays down. You lower the temperature, the resistance becomes smaller. You lower a little bit more the temperature, the resistance becomes smaller. And then at one point you lower a little bit your temperature, and then your resistance just drops to zero. Absolute zero. You have no resistance whatsoever. It's called the superconducting phase. Okay? And it's of the second order phase transition. It's continuous. It's not that you have some portions with high resistance, low resistance. No, you have pretty homogeneous resistance everywhere, and just at some point it disappears. So okay, we continue now to the topic of surface energy. And what I want to tell you about surface energy is that it's actually very important. Where we have already encountered surface energy, I remind you when we just started to talk about phase transitions, or basically when we had coexistence of several materials inside the same system, we started to ask ourselves whether the energy is extensive or not. And our conclusion was, yes, it's extensive, although there are some sort of interactions between different subsystems. And those interactions are coming through the surface between the systems. The amount of molecules at the surface is not big. Not big as compared to what? Not big as compared to the total number of molecules in the whole system. Now, even more than that, when we looked on the energy bulk, so the energy inside a system, as I divide the energy at the surface, what we have seen that it goes as n to the power of minus 1/3. So contribution of the energy at the surface to the total energy is minor. It's basically negligible. Okay? And this is why it does not have any effect or almost no effect on the extensivity properties of the system. But today I want to discuss some different aspects. So I actually want to discuss what happens to this, not what happens to the total energy, but I want to ask myself what happened to the surface between two phases or between two materials when I start to change things. And why it's important? Well, because actually what we have seen that when we look at the phase transition, the material becomes non-homogeneous and different phases starts to appear like small clusters. And when those clusters are small and not too big, the surface energy is actually what determines the cluster size, its behavior. When I'm trying to change the surface energy, something might happen to the properties of the bulk itself. Or, for example, when I have two phases, but one of the phases is very small. As I said, I have a very small bubble, okay, of air in a large portion of water. So then the surface energy might be already comparable to the total energy of the system itself. So what I want to describe today, right now actually, is how the energy of the surface is actually changing, and can we describe the surface as an additional component in our system. Think of the following example. I have two systems. I can say, well, I have two systems, or I can say I have two phases, and they are somehow well separated. Okay, there is not a big mixture of everything, and I have very good separations for system A, for system B, and this is my coordinate y. So I change my coordinate. I can go from bulk, where I have only type B here, it can be phase B or can system B, and I can go to phase A, which can also be system A. What I mean by system, think about it, for example, as two systems composed of water and oil. Okay? And this is my glass. I have water on the bottom, oil on the top. Water is heavier than the oil, and there is a very strict separation between them. And this separation line, I should say, is my surface. Right? This is the surface between the water and the oil. I can say, well, I can also have separation between the water and the air, or oil and air, etc., etc. But I will always have some separation line, okay, some separation line between the two systems. Now, in order to be consistent with what I told you before about the extensivity of the system, how I want to describe this line, well, actually here there is some molecules that actually contribute to this surface. There's not a lot of them, but there are some. This is, I know, from the molecular perspective. What is usually the width of the surface? For example, between water and air, it's only the order of 3, 4, 5 molecules, not more than that, but it's pretty strong. Okay. Now, from mathematical perspective, I don't want to deal with molecules at all. I want to deal with a bulk description, and it must be very continuous. So for mathematical description, what I actually want to say, this surface that separates the two systems is surface. It's just surface. It has no volume whatsoever. Okay? So for example, if my system is two-dimensional, the surface would be a line. If my system is three-dimensional, so I have volume here, I have volume here, my surface will be a two-dimensional surface. It has no width whatsoever, mathematically speaking, purely mathematically. From a physical perspective, there are some volume because there are some number of molecules in this direction. How exactly mathematically I can describe the position of the surface? Okay. So let's look on the concentration of the molecules at two different phases. So this is my coordinate y. And I'm going, for example, from a phase where I have water to a phase where I have gas. So the concentration looks like this. Very deep inside in the water, the concentration of the molecules is pretty high because it's water. This is rho of y. Okay. And it goes like this. At some point, it starts to decrease as I start to approach the surface, right? It will go down, and then it will stagnate again at some specific value. Okay? This is rho b, this constant value over here. I have a high concentration of the molecules inside the water. This is rho A. I have a lower concentration of molecules inside the vapor. And somewhere here, my surface is located. Because the transition is smooth, right? The transition is not really abrupt in the physical world. Why? Because I have several molecules over here. And the whole surface is not very strict. Okay? So this is what happens in the physical reality. And what I want to do is basically say, well, it's not enough for me. What I want is a very strict line that will separate between system A and system B, phase A and phase B. Call it YD. Now this what happens for two phases. I can say what happens for two systems. For example, water and oil, right? There are no water molecules inside the oil, or there are almost no oil molecules inside the water. So here I can look on the concentration of the water only, rho Z. And what will happen over there, again I will have a straight line, decrease, and zero concentration of water molecules inside the oil. But how much inside, I don't really know. I have to go a little bit into the oil phase, right? So here I will have rho water, and here I will have zero. And somewhere in the middle, I want to draw my separation YD. How you can do this mathematically? It's a little bit similar to the Maxwell construction that I already presented you before. Because think of it. This is Y. this is rho of y. Basically, I want to state that my profile, mathematical profile, is constant at rho b, okay, and it's also constant for the other system at rho a. The transition between the two systems, as I want to imagine it mathematically, happens abruptly. Okay? It's a straight line. So this is what I want to obtain. And this straight line is what defines YD. But in reality, the system is slightly different, as I explained to you. It goes like this. Okay. So you remember how I constructed the Maxwell construction? I said the integral over p dv was equals to this other area, that basically the area under the rectangle. So this is exactly the same thing that I want to state here. The area under this hypothetical profile, okay, so the area over here plus the area over there should be equal to the total area under the real profile. Okay? So let's call this rho h, rho hypothetical. What I want to say is that integral from minus infinity to infinity of rho hypothetical dy should be an integral of minus infinity to infinity of rho y dy. Why is that? What is the integral over the density? Rho is the density of the particles. The integral over the density of the particles is just the number of particles. So the number of particles in phase A plus the number of particles in phase B is the total of number of particles everywhere. And it should be exactly the same as the total number of particles when I'm using this hypothetical profile. Okay? I'm sorry. So this produces exactly the position of what? The position of my YD over here. Because how I plot this hypothetical profile? Well, I'm taking the values of rho b, which is equals to the rho y when y is very, very small in this direction. I'm taking rho hypothetical to be rho a when y is very, very large. Let's write this definition. So rho hypothetical equals for y smaller than yd, it equals to rho b z goes to minus infinity, and for y greater than yd, it equals rho a z goes to plus infinity. Okay? This is the step function that I have over here. This is rho hypothetical. Rho z regular, well, why am using z here? Well, because I'm already using y to describe rho h. But z is just behavior of rho y as a function of, instead of y, I'm just using z. Alright, so what do we know? What do we know? We know the following. That the number of particles in phase B is equals to what? The number of particles in phase B equals to an integral from minus infinity to yd of rho hypothetical y dy. The number of particles at phase A equals to an integral of from yd to plus infinity of rho hypothetical y dy. The number of particles at the surface, right? The number of particles at the surface equals to the total number of particles minus the particles at phase A minus the number of particles at phase B equals to, this guy is simply an integral, let's write it separately on the board above. So n is just the integral over rho y dy from minus infinity to infinity. Okay, let's write it over here. So n equals an integral from minus infinity to infinity rho of y dy. Na, we already know what it is. Nb, we also already know what it is. So we have that the number of particles at the surface equals to an integral from minus infinity to infinity rho y dy minus an integral from minus infinity to yd rho hypothetical y dy minus an integral from yd to infinity of rho hypothetical y dy. And what we obtain, that the number of particles at the surface, if we use the surface as a very separate specific point or specific line, okay, one-dimensional or two-dimensional, it equals to an integral of minus infinity to infinity of rho of y minus rho of h dy. Okay. And what we want to state is, as long as we have only one component, okay, one type of particles, or we have one type of particles and none other type of particles, is that we always can pick a specific yd such that this integral is equals exactly 0. Okay? And this is the definition of our surface. We want to define it mathematically. And we say, well, the number of particles in the surface is 0. If we take the surface as a line, at which point? At the point yd. Now, why does it help us? It helps us when in a second we'll define the total energy. And for the total energy, the energy of the surface won't depend on the number of the molecules at the surface. It will depend on other properties, maybe elastic properties. But it won't depend on the number of molecules at the surface. Why? Because for a surface between two phases, we can always choose this surface in such a form that the number of molecules at the surface is strictly 0. So let us look on the energy of the surface. What is the energy of the surface and how we define it? So first of all, we want to state the following. What is the change at the total energy of the system by, when we change what? When we change the surface area. Okay, so we, in 3D, and the surface is now some two-dimensional thing, because we chose it this way, the number of the molecules inside the surface is 0. What is the change of the energy if we change the surface area. We change it locally. We bend it a little bit. It was straight, and we increase the size a little bit, right? We stretched it a little bit. We compressed it a little bit. The surface itself, not the whole system, but only the surface. So we can say that the energy, well, can change, right? Maybe it might be a small contribution, but the total energy can change when we're keeping S, V, and N constant. And it should be what? It should be some. Not constant, but we call it this guy, this derivative as gamma. And this is the definition of the surface tension. Basically, we use another parameter to describe the energy. This parameter is the surface area. We say, well, the energy will depend on the surface area. Okay? And what we know, or what we define, is that the derivative of the total energy with the surface area is what we call the surface tension. So if we write what is the change in the energy, there is TdS, as usual, minus PdV, as usual, plus mu dN, as usual, right? This is the usual description of the bulk. We also say, well, we have a surface here. And for the surface, we plot plus gamma d sigma. Sigma is the surface area. Okay. Is gamma greater than 0, smaller than 0, positive, negative? Gamma is positive, negative. What do you think? You think it should be negative or positive? So how we should think about this question? What we know about energy? The only thing that we know about energy, well, we have all the stability criteria, but we know that the energy should be at a minimum for a system. Given an equilibrium, so assume I'm sitting in an equilibrium, the energy is actually in its minimum. Everything that I change a little bit increases the energy. Okay? This is the variational principle that we obtained from the second law of thermodynamics. So if my changes of the energy are described by this equation, okay, and gamma is negative, what will happen? What will happen is that, well, I have a specific surface, gamma is negative, I increase this surface a little bit, the energy becoming smaller. So it's good if gamma is negative, it's actually good to increase the surface. So I will increase the surface a little bit more, it will decrease the energy. Well, it's very good, the system will go into this direction. So we'll increase the surface area a little bit more, and a little bit more, and a little bit more. By increasing the surface area, I am decreasing the total energy of the system if gamma is negative. So what will be the final equilibrium? The final equilibrium will be when the surface is very, very large, is at its maximum. So basically, eventually, I will reach the situation that everything is a surface. It's not this. Everything is a big surface. It's not that type A and type B. There's a huge mixture of everything. So there is no separation between those two phases, or no separation, no mixing between those two systems. This will occur when gamma is negative. This is not what I see. What I see is that surface is staying constant. I don't have mixture. It's not that surface is actually occurring everywhere in my system. The surface occurs at a very specific position. It might be wiggling a little bit, but it's very specific. What it means? It means that gamma is always positive due to minimal principle for the energy. Because otherwise, the energy, if gamma was negative, the energy would become smaller and smaller and smaller and smaller and smaller. Eventually we would have no phase separations whatsoever. So the surface tension, the gamma is the surface tension, is always positive. Is always positive. Now think of it. What is the surface? What we are saying by changing the surface area a little bit. So from this definition, dE is dds, and all of this is dW, right? The amount of work that I perform. So if I haven't changed the number of molecules, and if my volume have not changed, gamma d sigma is dW. What is the amount of work that I performed? I remember I'm calling this is a generalized force, and this is my generalized coordinate. Okay? So when I'm changing the surface a little bit, gamma is the generalized force that tries to oppose those changes. Okay? So if this is my surface, okay, and I'm trying to push on my surface and change it locally. Okay, at some point, it's a straight sheet, and I'm trying to push it a little bit. In order to increase the size, it will increase eventually the size of the surface. I can say, well, I can think about it, some sort of an elastic sheet, and this elastic sheet will oppose any force that tries to make what? To perform local changes in its form. So this is what happens. This is why the tension, the surface tension is positive. I'm trying to change locally, to bend the surface a little bit. The surface opposes it and it tries to push back. Gamma is this effective force. I can call it an effective force. It doesn't have force identity. But gamma is the general force that tries to oppose local changes or global changes at the surface area. So this is sigma. This is my external force. The local force that will oppose those changes are exactly gamma, the surface tension. Think about it. You have a glass of water. Okay? You have a glass of water. Here's the water. You place a needle inside the water over here. It will just sink down. Nothing will happen. Why? Because there is gravity. You place the needle, the same needle, on top, exactly on the surface. It won't sink down. It will just float. Why? Well, the buoyant force is different? No, it's exactly the same. The weight of the needle is the same over here as it's over there. So why does not the needle does not sinking when I place it on top of the water? Because of the tension. The surface tension of the water has an additional force. Okay?
But if the needle touches the surface, that will create a new surface.
So now it tries to break the surface. So think of the needle, it's a very small object, right? If I would try to place something big, it won't happen. So it touches in only very small portions of the surface, right? Think about this. Let's look on the side. So this is water, and here I place my needle. It goes like this, okay? I place it over here. What it tries to make, it tries to break through the surface over here. It basically bends it. The surface will start to bend around my needle. If I'll just look at this under a microscope, this is my needle, and this will be my surface. Okay?
So there are still air between.
And this is air. No, there is no. There is almost. This is an interesting question. how much air molecules do I have between the needle and the water? There's almost no air. But this is this is interesting. I don't think that there is any air. Yeah, but there is a very interesting physics over there. So, but here's air, this is water, and this is very small, and it contains almost no water. But this is still a surface in what perspective? I'm thinking of this needle as something really, really, really small. Okay. When it's huge, it's different. But what happens? I try to bend this water. So think about a string. I have a string. I am pulling it, and then I'm trying to push in the middle. Okay. What the string will try to do? Try to push backwards because it doesn't want to change. It doesn't want to increase its size. Okay. This is what happens to the interface, to the surface. Okay. Although there is molecules, this is not a string, but this surface will have to try and push backwards. Okay? And this is the additional force that acts on the needle and prevents it from sinking down. Alright, so we can think of gamma of this tension as some sort of an effective force. It's not having the units of the force, but in our perspective it's basically the same. Okay. Now, if this is our energy, we can take out of it and separate from it the energy of the surface itself. This is the total energy of the system. Let's take out the energies of system A and system B out, and what we will be left with are only energies of the surface itself. Are only energies of the surface itself. Okay? So what we know? We know that the energy of system A is basically TSA minus PVA plus mu NA. E of B is TSB minus PVB plus mu NB. What we can do now is we can take out of E, we can subtract EB, and we can subtract EA. Okay. And we will obtain the energy of the surface, or we can take dE minus dEB minus dEA, right? And then what we will be left with is dES. Why? Because EA plus EB plus ES equals the total energy. So let's take the total energy, subtract from it the contributions that are coming from system A and system B, and eventually obtain the contribution that is solely from the surface over here. Okay. Now remember that NA plus NB is the total number of particles. VA and VB is the total volume. So DEA is TDSA minus PDVA plus mu DNA. DEB equals TDSB minus PDVB plus mu DNB. Okay, DE, we already know what it is. What is DE? DE, there I have it. So we have here, what is DE? It's TDS minus PDV plus mu DN plus gamma D sigma. And DE minus DEA minus dE B eventually equals to T ds B ds surface, because the only thing that we left is the entropy of the surface, minus P, I'm sorry, and only thing that it plus gamma d sigma equals DES. Why are those the only two terms that we have left? Because dV equals dVA plus dVB. V equals VA plus VB. And dV equals dVA plus dVB. The same goes for N. N equals NA plus NB. We already used this option in order to define where the full surface is located. So dN equals dNA plus dNB. We don't know what happens for the entropy, okay? But those terms are disappear as those terms. What we left with are the entropy contribution and the surface tension contribution. So dE surface is d entropy that is associated with the surface plus gamma d sigma. And I can go back to your question over here. Does it matter if there are air molecules or water molecules? It is matter. It does matter. But from the homogeneous perspective, I'm looking on the surface as something that is not water and not air. It's something else. And it has entropy, this mathematical construction, and it has an elastic energy. Okay? And I wouldn't care if there is only water or only air. I do in real physics. I will do. Non-homogeneities change everything. But from this homogeneous perspective of thermodynamics, I don't care. Okay. Okay. So this is a homogeneous function. So by implying earlier first theorem for homogeneous functions, we know that the energy of the surface is temperature multiplied by the entropy of the surface plus gamma sigma. Okay? And from here, we can obtain the definition or the value of the surface tension, which is E minus Ts divided by sigma. What is E minus Ts? Is the Helmholtz, it's the free energy, okay, divided by the total area. So what we can say, the surface tension is the concentration of free energy per surface area. Okay? This is the definition of the surface tension. All right. So for now, we managed to separate two phases or two systems. Okay? We can, for any two kind of phases, we can create a single surface, and on one side will be phase A, on the other side will be phase B. Or two different materials like oil and water. We can separate them both. We'll have oil on one side and water on the other side. When I have already three materials, three type of phases, I can no longer do this. So three types of particles, right? I can no longer say, well, there is particles A on this side, particles B on this side, where I put particles C. They have to sit also in the middle, okay? So what happens when we add additional type of particles to the system. What happens to the energy? To the energy. So remember, for the energy we obtained that when there are only one type of particles, or two systems basically, that the energy of the surface to the energy of the surface here, of the surface. So the energy of the surface, which is written over here, now rewrite it, it depends only on the entropy on the surface and the area on the surface. And we were able to neglect all the contributions from the volume and the presence of other particles, etc., etc. But when we add additional particles, okay, when we add additional particles, some of them can sit exactly on the surface, right? Although the system, the surface is two-dimensional, if we're talking about 3D, so the surface is two-dimensional. It has no volume. It doesn't matter if I add additional particles. It has no volume. But some of the particles, this is B, this is A. I have a surface between them. And particles B sit only here. Particles A sit only there. And if I add particles, and how I know this, because this is how I constructed my surface. This is YD. This is how it's constructed. But if I add particle C, they can be everywhere. Okay? And then basically particle C can be, some of them can be on the surface itself. Okay? They are small squares. So when I'm considering system that it's constructed from two particles, from two systems, oil and water, water and air, I can have a very strict mathematical separation between the two subsystems. But when I add additional particles, the third type, this equation already won't hold. What will happen? V, it has no volume, so V won't add up. But there might be a contribution for the chemical potential. So when I add additional particles of type C, I will get that my surface energy is contribution from the entropy plus contribution from the elastic term, gamma B sigma, and I also need contribution from the presence of additional particles, mu C dn C. Why? Because they can sit exactly on the surface. Although the volume of the surface is 0, but, well, as I'm plotting here, the particle is just sitting in the middle. I can apply again the Euler theorem, okay, and E of the surface goes like ts surface plus gamma sigma plus mu C and C. What is NC? The total number of particles at the surface. Let's obtain from this guy a type of Gibbs-Duhem equation. So let's take the differential of dEs. So dEs, now it's the differential of whatever stands over here. ds surface plus gamma sigma plus mu of type C and of type C. It equals to t ds s plus s s dt plus gamma d sigma plus sigma d gamma plus mu c dn c plus n c d mu c. So this is des. But des is also what we have constructed over here. Okay? So we know that t ds s plus gamma d sigma plus mu c dn c equals to this guy. They're exactly the same, they must be. But when I have this equality, this guy goes with this guy. This guy goes with this guy. Okay, what is still left? This disappears with this. And eventually, and this is how I obtain initially the Gibbs-Duhem equation. What I eventually get is that S dt plus sigma d gamma plus n c d mu c goes to 0. Why I'm doing this? I only want to introduce some additional particles, and I want to see what when I'm looking what happened to the energy. What I'm interested in doing is to see how the tension of the energy is going to change if I'm adding additional particles to the system. Right? This is what I'm trying to do. And here you see I have d sigma. So from here maybe I can say, oh, how the, not sigma, d gamma, how the surface tension is going to change when I'm changing what? When I'm changing the chemical potentials or the number of the particles on the surface itself. And it will be clear to you in a second why I'm doing this. So let's look on the situation when dt isothermal, when dt equals 0. Let me just erase this part, I will need this. So when dt equals 0, the only thing that I have left from this Gibbs-Duhem type of equation is a connection between d gamma and d mu. So we have sigma d gamma plus nc d mu c equals 0. Or nc divided by sigma equals to minus d gamma d mu c. This guy is greater than 0, right? Sigma is the surface area. NC is the total number of particles of type C that are sitting on the surface, so it's positive number. This guy is positive, which basically means that d gamma d mu should be always negative. But what is d gamma d mu? what is mu? We can say, well, mu d gamma d mu, can say that is d gamma d rho c, the concentration of C, multiplied by d rho c by d mu c. Why I'm doing this? Because this I already know what it is. This is the concentration of particles of type C with d mu c. Remember, the chemical potential is the thermodynamical force. The higher it gets, the more particles I have. So the higher is mu c, okay, the higher is the concentration of particles C. So this, we already shown this, is always greater than 0. Okay? So look, now what we have n of C divided by sigma greater than 0 equals minus d gamma d rho C multiplied by d rho C d mu C. Everything here is with a constant temperature. Why constant temperature? Because I have taken an isothermal process. So this is greater than 0. This guy is greater than 0. Okay? Higher chemical potentials, more particles. More particles, higher concentration. What we obtain is that d gamma d rho C at constant temperature is always negative. What we have obtained here? We obtained that the surface tension decreases as we add additional particles to the system. This is a very interesting observation, because we use this property on a daily basis again and again and again and again without understanding this. But this is a fantastic feature. If you have a surface and you want to maybe kill it, okay, dismantle it, what you have to do, you have to add additional particles, surfactants. That basically will contribute, that what they will do, I will add additional particles to the system, and those particles will decrease the surface tension, and when they decrease the surface tension, at some point there would be no surface tension or no surface whatsoever. Very simple example. Take a glass of water and spread some pepper over it, or paprika, or whatever, some small particles. What will happen? They will float. Do it at home. It works great. Okay, so take a glass of water. Take a glass of water. It has water inside. So let's make it blue. You have water inside. Here is water. You spread the pepper on top of it. It floats. Why it floats? Because of the surface tension that I've already told you. Okay, fine. Add some salt to the system. So, no salt. You add some salt to the system. There are additional particles. Okay? Now there are additional particles with soap. You add additional particles. You again spread the pepper on top. It won't float. It will just sink. What happened? The surface tension had decreased. Remember what I explained? Why the stuff is floating on water and is sinking inside the water? Because of the surface tension. Now, I've changed the concentration over here. I had added soap molecules that some of them are sitting on the surface itself, and they like to see it on the surface. The soap will like to see it on the surface because soap molecules have hydrophilic heads and hydrophobic tails, so they would like to concentrate on the surface. And what will happen? We add particles to the surface. And as we add particles to the surface, this equation tells us the gamma, the surface tension, starts to decrease. You add more soap, the surface tension decreases more. You add more soap, the surface tension decreases more. And at some point, when you add enough soap, it won't hold those pepper molecules anymore, these pepper particles, and it will just cross it and get to the bottom. Okay? This is nice. But it immediately also tells us something else. Well, if by adding of soap, the surface tension is decreasing, and by adding some, it doesn't really matter what I add. This equation always tells us, no matter what you add to your system, as you have more particles sitting on the surface tension will decrease. I can learn something about bubbles. Do you know how to make bubbles with water and soap? Right? You know, everyday life. You have some water. Try to make bubbles out of just water, plain water. It won't work, right? You cannot produce any bubbles with simple water. Why it won't work? Because the surface tension of water is too high. When I'm creating bubble, I'm just flowing air on the water surface, okay? It won't float. Why it won't float? Because there are very strong forces that are preventing it from floating. Okay? It will break maybe, but it won't float to a big bubble. I'm adding soap molecules. What happens? The tension at the surface becomes lower. So now I'm trying to press on it, it changes its shape because the tension is really, really, really small compared to the water, surface tension. Okay? And as I now have this tension which is small, I can produce bubbles. And actually, when I also add some glycerin inside it, I can produce surface tensions that's very, very flexible and produce bubbles the size of this room. Okay? It's just fantastic. And all based on this criteria that no matter what kind of particles I add to the system, the surface tensions becomes smaller and smaller and smaller and smaller. Okay. Now, another daily life experience that we have, you wash your water with soap. It's again, this water, oil, soap, it's just a great example. Why you wash your hands with soap? Why it's not just good to wash, well, for example, place your hands inside of a jar with oil, okay? And then just try to wash it with plain water. It won't help. Why not? Have you ever thought about it? This is exactly why. This is exactly why. Because if you have oil, very thin film of water or oil. So for example, your hands are dirty. It's basically you have a lot of some oily substances on your hands. Okay? And you have water. Okay? Those two guys, even so the film of the water is small, so the water is flowing, it does not mix. Okay? So water is incapable of washing your hands if it have some oily elements, right? Why it's incapable? They don't mix. There is a surface between them. The water cannot separate, cannot penetrate. What you do when you add soap into this problem? So when you add soap, you have molecules. Those soap molecules that are very smartly designed. They want to sit with their heads inside the water and the tails inside the oil. So you explicitly add some molecules, not everywhere, well, but they want to sit at the surface. They just want to sit at the surface. Okay? So what happens when you add them? So you add a little bit, the surface tension decreases. You add a little bit more, the surface tension decreases. At some point, as you add more and more and more soap, the surface tension becomes zero, right? Becomes very, very small. So then, when it's very, very small, it's really easy to break it. And then mixing starts to occur between the water and the oil because there is no surface anymore. Everything is mixed, right? This is what the thermodynamic limit tells us. Things will start to meet, the surface will break down. And this is why we're capable of actually washing our hands, because the surface tension is decreased by the presence of the water molecules. Now, thermodynamics doesn't know anything about molecules. Anything. It just knows that if I contribute another type of particles, eventually the surface tensions must go down, and eventually the surface tension will break. What will happen on microscopical level? Thermodynamics knows nothing about it. It can tell us very general things. It doesn't understand what's going on here about hydrophobic and hydrophilic tails. Nothing. But this is very, very strong. It just tells us at some point it will break. So introduce particles that will sit on the surface, okay, and it will break down the surface. What happens with the surfactants? So how those guys start to break? Well, at some point when this separation between the different molecules is not too big, it becomes easy to bend the surface. It becomes bendable and breakable. At some point, the mixing occurs in a very interesting fashion. So you will have oil inside. You will have water outside. And it's mixed. How it's mixed? It's not exactly mixed. It's not mixed. So those molecules, they start to create very small bubbles. Okay, very small bubbles of oil inside the water. How those bubbles looks like? So there's a lot of those molecules. They have these hydrophobic tails inside the oil, and they have this hydrophilic heads inside water. Okay. And this guy is on the order of 100 molecules, not even less, 50 molecules. So it's really, really, really small. So there is no surface because there is no microscopic structures. The surface have disappeared. It's not exactly true. From microscopic perspective, there are small surfaces everywhere. And those small surfaces are separated, and this is how water washes the oil away, right? From the thermodynamical perspective, well, the surface just, you got rid of it. It's not exactly true, because microscopical perspective tells us something different. And it's very interesting how it happens, right? But from thermodynamical perspective, we can just completely break the surface and then, well, eventually wash our hands.